years ago, and that works well for the C-based work that we do. More recently, we started using it with the Tcl-based code that we have, and it works technically, but it doesn't give good results because it's just giving us C call stack information, which is not real useful. So in the interest of appeal to authority, refer to Richard Hamming. The purpose of computing is insight, not numbers. We're able to generate lots of numbers when we're doing profiling, collecting samples and that sort of thing, but if we don't know what that means, it's not terribly useful. So I'd like to, just a brief overview of what I'd like to talk about today. What's the problem? Why is it interesting and important, at least to us? The key components of the approach that we used, results, go through an example, shows what we did, some notes and limitations, and future work that might be considered. So the problem is that we want our programs to run correctly and to run fast. Once we've got them running correctly, how do we make them go fast? And one of the primary ways is to do analysis of running program, to sample the call stack and do collation of the results. To be most useful, the where needs to be referring back to our original source code. The problem that we faced with the combined Tcl C programs is that everything is turned to C, which is not what the application developer is working in. So an example of profiler use, on the left side there's a trivial C program, routine main calls do sum or do prod. Three possible call stacks that you might think about if you were to interrupt the program execution at any given time. One is that execution might be just in main. Another is that it might be called through main into do sum. The other is that through main into do prod. When we collate the profile results, instead of a series of stacks, we make a call tree. So in this case, we have main with two children, do sum and do prod. So the sort of results that we calculate are shown there. In this case, I coded this example up into our program and profiled it. There were 1,489 samples in main and its children calling through. We note that do sum and do prod called about the same amount of sample. And at first I was a little surprised at that. I thought that, well, the multiplication would take a lot longer than the addition. But on reflection on it, modern processors have multipliers that are able to do that pretty quickly. So it seems reasonable that an addition sort of thing and a multiplication sort of thing take about the same amount of time. If we're to look at the same sort of thing using a Tcl program, on the left in the blue text there is essentially the same code, but if we were to look at a C call stack for that, it's got a bunch of TCL splat sort of things, which is it's wonderful code, but as an application Tcl developer, it doesn't help me understand where I'm spending time and things. So the problem that we face is how to get the C and Tcl put together to be able to make sense of sort of things. Existing profilers do one or the other, but not both together that we're aware of. So what we want to do, or decided what might be reasonable to do, is to convert some of those TCL star sort of things into the actual Tcl command that's being executed at that moment. The information on the C call stack is insufficient to do that. That we have these two things kind of side by side. The way that we chose to do it, there's probably others, is to maintain a copy of the Tcl call stack during program evaluation. And then during the processing of the C call stack, we can integrate these together to get something that makes sense in our application. Diagrammatically, this is the sort of thing that we do. In the upper left, we use the obj trace capability. So we register a function, save command, and that save command is called on every Tcl command that is executed, and we save the command that was stored at the appropriate level into Tcl stack. That's a small amount of memory. I think we made our stack 300 lines long. They're 80 characters apiece. During profiling, interrupts are set up periodically. That's the little alarm clock with the lightning bolt coming out of it. Process call stack is called at each one of those interrupts. Its job is to retrieve the cease call stack. So that's this business here. And then at that moment then we have both the C and tickle call stacks, and the job of process call stack is to integrate these two together to make sense of them. I apologize for the source code here, but it was probably the most straightforward way to explain it. On the left, process call stack has just a big while loop in it that it's just looking at each entry in the call stack, and there are three possible outcomes for what it can do. The first one is if it's a tickle eval obj internal, it will go manipulate that item from the tickle stack. If it's a different TCL star or on-tickle star, or there's a variety of other things that we filter out, we ignore them, that they're not important for the sort of application level stuff that we care about. And then finally at the bottom, other C functions are just saved verbatim. They're part of our code, that's stuff that we wrote that we care about. Going back to the tickle eval obj internal, there we call the format tickle command, and then there we have a number of rules. We tokenize the command that we saved, and we'll look at various of them. If it's at the F or a 4, those things weren't important to our understanding where time was spent, so we just filter those out. Others, like the info and winfo, will combine that with the sort of sub-command that's involved. And there's other rules that you can see there. So putting that all together will condense down C call stack into something much more reasonable. We'll walk through an example in just a moment. The example that I found, which was useful, is using the top-to-column command. That's procedure that's just part of the QuestaSim simulator. Its job is to take an input stream to tokenize it based on rules from the particular language. In this case, it's Verilog. We can see on the second to bottom line there, pulling up column 23, and I just used a bogus line. The quick round fox jumps over the lazy dog. And we call it a million times in order to have it run long enough such that sample would be distributed across where it was spending its time. If we look just at the C stack, we get something which is rather indecipherable. There's 150 lines, so this is 1.5 pitch font, so I don't expect you to be able to read it. But this is what a standard call stack looks like, so that wasn't terribly useful. Of the 150 lines, there's about 6 of them that our application developer cares about, and they're called out there. So the tickle prim top to column is the C implementation of the top to column proc, and some of the child functions associated with it. And you can see the numbers of the samples there. So this is, as it stands right now, it doesn't lend a lot of help to the user. Call stack mapping detail, we just talked about process call stack. This is an example of going through it. On the far left column is a C call stack. In the middle is the operation the process call stack function does. And the right column is what we end up with at the end of this process. There are about 100 lines on the C function side, and we distill it down to 11 lines. So we can just look at a few of them there. The first 3 come across without change. Then there's a bunch of TK and TCL sort of things, and we say, no, we don't care about that. We get down to the red line there, tickle object internal. That maps to a tickle command, vcop plus action. And we can see going down there, there are further mappings that we do to tickle commands. Continue on the next page. And here we can see that we pick up the do work, which was part of the tickle code that we cared about, do work 2, top to column, and the things that it's done. So we condensed down 100 lines into 11. When you roll that up into a call tree, we get profile results that look like this. And the notable feature here is that we've got a mixture of C and tickle things. The items with the little white icons with the C in them are C code, and the little reddish sort of things are tickle code. We can see in this case that time do work calls do work 2, do work 2 calls top to column. And if we look in our result here, we see that sort of relation. Then if you look at children of top to column, it's the tickle crib top to column. His children are lang to lang type, and HDL takes to the column. So we can see this pretty easily now. This is a screenshot from a hierarchy widget that exists in our program, so it was easy to adapt to that. With this sort of a view now, we can look at this and say, what's going on? Now we can easily find dysfunctions that were important to us. When we look at the time spent, we see that we spent, 2,200 samples in top to column, 2,140 in the tickle creme top to column. And then we look at the children of that, and we see that lang type takes 1,900, but the HDL text to column takes 228. So we're spending 8 times as long to figure out what language we're processing, which was an argument passed directly in, versus doing the actual tokenizing. So we can ask the question, well, why is the language type thing so slow? We can look here and see that top to column calls C code. Oh, that calls back into tickle code. This is interesting. If we look at the code for that, we see that we're filling a text buffer. Is it Vhdl language? Is it Verilog language? At the bottom, we have the corresponding tickle code that gets called. So we're just doing a string compare, what we call Verilog language, just to return a string. So that's the sort of work that goes on there. Looking back to this, if top to column is a performance bottleneck, we can say, oh, we're spending a lot of time just trying to figure out that that Verilog string maps to some manifest constant. So if we wanted to speed this up, we could just move the tickle access, make that function we looked at, lang to lang type, which work in C, and we cut out a lot of the overhead. And this is the sort of thing that accidentally can creep into a program, and being able to do profiling like this can highlight issues like that. So we found it useful internally in our application development. So a few notes and limitations. Performance is slower while we're doing this profiling. We're spending the time to keep our tickle stack up to date. So that's a cost, it's a tax that we pay, but it lends us that insight, so it's a worthwhile thing to do. When we do the tickle create outage trace, we found that if we did allow the inline compilation, we weren't getting correct correlation between the tickle stack entries and the C stack entries, so we turned that off. That wasn't available to us. We made a few changes to the tickle core on the save command that was called back. We used the num levels to know at what point of the stack we are, and we made a few changes that are completely compatible with the core, so maybe some of you that could help understand what a better way to do that is. The save command, the one called let it create outage trace, wasn't always called at the right time, so there was occasionally gaps in the system, so I'm not sure about that. And finally, the process call stack does some filtering we talked about, and then different applications could have different uses of that. On some future work, Tickle 8.5, it would be useful for this sort of thing to have a lighter way of knowing which commands were being stored, that there's mutexes that get set up and torn down, that sort of stuff. So in 8.5 it would be useful. I'm not sure that there's great interest in pursuing that. In Tickle 8.6, as I understand it, I've not explored it, there's stackless evaluation. And that is a whole different mechanism, and if we wanted to pursue this, it would require some sort of a different approach. So we found this to be a useful sort of thing for understanding where time is being spent in our tickle code. Thank you for your attention. Any questions?
You're tracing so as to save the call stack, but surely the tickle interpreter knows its call stack already because we can introspect.
Right. So that was, yeah. I think the primary reason that we chose not to do that is due to the variability of where interrupts can come. The profiler is just strictly time-based, and it'll be, it doesn't care where your program is. So if you're in the middle of a memory allocation or something, it's kind of a delicate place to be, and we're doing this process call stack and sort of stuff. And we didn't want to run the risk of doing something that was going to kind of teeter us into a bad space. Whereas if we store the command as it's coming through, we know that's all just static memory. We can do that pretty easily. So that was the primary reason. That said, if there was a reliable way that we could just retrieve the call stack and be able to correlate it where it belonged, the appropriate places in the C call stack, that'd be swell. That'd be great. So,
are you going to, I mean, is this just an internal tool? Or?
this is an internal tool. Yeah, we invested in a profiler infrastructure, and the work that we did here was extending it to be able to get better insight into where our typical code is spending its time. So, yeah, there's no plans to try to generalize it, I'm afraid. So, okay, thank you very much.